Now let's go to algebraic simplification. So there are two methods in simplifying our algebraic expression, which we have derived from our truth table. So first is using the Boolean algebra. So this is using the Boolean algebra theorem for the identities that we have discussed in the previous chapter on Boolean algebra. And the second one is on Karnaugh mapping, which we will be discussing the step-by-step approach later on. So first, let's just go to the Boolean algebra simplification. So this can be done in three ways. First is by grouping. Second is by multiplication of redundant variables. And the third one is using the De Morgan's theorem. So let's have first B, algebraic simplification using the grouping method. So in this example, we are given an equation or an expression A plus AB plus BC. So if you have noticed in the given example or the given expression, the first and the second term, there is a common term, which is A. So in the first term, we have this A. In the second term, we have this also A. So in the method of grouping, just like in our common algebraic expression, we can group these two, A plus AB plus B and C. So what is common in this group is the coefficient A. So we have A. So if we will group A from these two expressions, what remains is 1 plus B plus BC. However, from our truth table, what is the value of 1 plus B? So if we will look into our truth table or our Boolean identities, under the dominance identity, A plus 1 is equal to 1. So any variable added to 1 is equal to 1. So going back here, 1 plus B is just equal to 1. So 1 plus B is equal to 1. So therefore, this becomes A times 1 is equal to 1. And here, any identity or any variable multiplied by 1 is the same as the variable itself. So A times 1 is just equal to A. Therefore, the minimized form is A plus BC. So the simplified form of our equation, A plus AB plus BC is equal to A plus BC. So that is our simplified form. Next, the second method of algebraic simplification is by multiplying of redundant variables. So we have here the sum of the notes. Multiplying by terms of A plus A bar does not alter the logic. Why? If we will multiply the terms with A plus A bar, it does not alter the logic. Why? Let us see in our Boolean identities. In our Boolean identity, a plus a bar or any variable added to the complement of that variable according to this complementary principle, a plus a bar is equal to 1. So that means multiplying the term with a plus a bar or multiplying it by 1 does not alter the variable or the equation itself, or it does not alter the logic. So such simplification by a variable missing from a term may enable the minimization. So it may enable the minimization. So let us have this example. So our given equation is AB plus AC complement plus BC. So what we have done here is we have introduced or we have multiplied C plus C complement to the first term, to the AB. We have multiplied it to AB because we said the value of this C plus C complement is equal to 1. So AB times 1 is just equal to AB. So choose only one from the terms so that we could simplify the term itself. So multiplying so why C plus C complement? So please take note that in here, we are to multiply a variable missing from a term. So in our first term, A, B, the missing term, because we have here the constants A, B, and C, you can see that in the given, may A, B, kag C ang ating inputs. The missing variable is C. That's why we are to multiply C plus C complement. Why not A? Because A is already present. Why not B? Because B is already present. So we will be multiplying the missing variable from the term. That's why we are to multiply the C plus C complement, which is again, according to our complementary property in our identities, in Boolean identities, it is equal to 1. So again, you copy the second term, A plus C complement, and you copy the third term, B plus C complement. And then what you will do, you apply the distributive property. We have AB times C is equal to ABC. Then we have AB times C complement, so plus ABC complement plus AC complement plus BC complement. After that, what should you do? You, you rearrange the term. We rearrange the term so that we can again apply what we have learned in lesson 1, which is also the grouping. So this term could be rewritten as ABC plus BC plus ABC complement with as ang complement, ang C lang may complement. ABC complement plus AC complement. So we rearrange the terms so that it would appear just like this one. And then we will group. What is common here? The common here is BC. So we will factor out BC. What remains is A plus 1. What is the common here? Plus A. C complement is the common. What remains is B plus 1. So This is it. And again, according to our theorem, a plus 1 and b plus 1 or any uh, variable added to 1 is equal to here the dominance principle. A plus 1 is equal to 1 or any variable added to 1 is equal to 1. So this becomes 1. So the value of this one is 1. The value of this one is also 1. Therefore, BC times 1 is just equal to BC, and AC complement times 1 is AC complement. So that's how we simplify using multiplication of redundant variables. And again, let me just emphasize that in multiplication of redundant variable, you multiply a variable that is missing from the term in order to enable the minimalization. So the third method is the method of De Morgan's theorem or application of De Morgan's theorem. So the application of De Morgan's theorem, of course, De Morgan's theorem because it was discovered by De Morgan. And what does the theory say? So, but first let me explain the De Morgan's theorem expressions containing several inversions stacked one upon the other may often be simplified using the De Morgan's theorem. So De Morgan's theorem unwraps the multiple inversion process. Now let's take this example. We have A B complement C plus A C D complement plus B C complement. So we will apply De Morgan's theorem to simplify this expression. So in De Morgan's theorem, uh, we simply have to, if we will look at the identity. The identity is A plus B is equal to A complement times B complement complemented, while here your A times B is equal to A complemented plus B complemented complement. So if you will notice in De Morgan's theorem, while we are while the given is plus, in the simplification it becomes multiplication. And while the given is multiplication, the output becomes addition. So in the Morgan's theorem, we are following this rule. Break the bar, change the sign. Or otherwise, sometimes we also have, if you want to make the bar, we also have to change the sign. So this is the rule that it is followed in the De Morgan's theorem. You break the bar. If you wanted to break the bar, you change the sign. Or if you want to make a bar or make the bar, you also have to change the sign. So let us apply this rule in this example. So first, let's consider the first bar here, the one that is below the longest bar. We will consider these two bars. So what is the rule? If you want to break the bar, you change the sign. So first, let us consider the A, B complement C. Then this term is being complemented. So the rule says if you want to break the bar, we will break this bar. We will break this bar. So you have to change the sign. So from our theorem, this is multiplication. Then we will change this one into addition. But if you we will break this bar, so it becomes A plus B complement plus C complement. But take note that we have to break the bar. So ang complement sa babaw, break natin. So the long, the complement becomes break. It is broken into three. You break the bar, but we have to change the sign from multiplication to addition. So we have broken the long bar, so it becomes addition. So if you will simplify, this is A complement plus what is B complement complemented according to our theorem on the involution, double complement is equal to uh, the quantity itself, or that means two negatives become positive. So that also applies here. The complement of the complement becomes positive. B plus C complement plus C complement. So that is the term here. Next, we will break the bar again of A, C, D. We will break this bar. So this is equal to A complement plus C complement plus D complement. So this is, you break the bar, we break this bar, we break this bar into three, but we have to change the sign from multiplication to addition. So this term is this term. And then we copy the BC. Now, looking back, so here, these terms here, we have common A and C complement. So we have rewritten, or we have simplified these two terms into this term. Common is A complement, so we just write A complement. Then we have B, and then we have C complement because it is common here on the two, and we have here D. Plus, of course, our last term, BC. Next, let us again simplify this one. So now we have complement plus B plus C complement plus D plus BC. So again, if you will look at these terms, we have B here and the BC here, which is common, so we can rewrite A complement plus C complement plus D plus B plus BC. BC complement. I mean, it's BC complement here. So here, we can apply the grouping. And of course, this is B times 1 plus C complement. And again, this terms is simplified into 1. That's why what remains is A plus C complement plus D plus B. Or simply, that's why that is the term here. But take note, we have not yet simplified the, ano, we have not yet simplified this, we have not yet simplified this long bar here. We have not yet simplified this one. So again, applying the rule of De Morgan, if you want to break the bar, you have to change the sign. So we will break this bar, the yellow bar. So if we want to break this bar, we have to change the sign. Again, so since this is positive, we are to break the bar, we have to change the sign. So we have to change this plus into again multiplication because we want to break this bar. We want to break this bar. Breaking the bar, it becomes a double, then times because change the sign, B bar times C double bar times D double bar. Do we have a D bar? Sorry, this one is D bar. I mislook at the given na ano nila na yun. Because when circled, nalipatan ko nga may bar ang D. So it becomes D double bar. So here again, it we want to break the bar, the longer bar in the yellow. So it becomes this one. Again, with our involution theorem, the double bar becomes positive. So that's why A double bar is A times B bar plus C double bar is just equal to C. This is times. And then D double bar is equal to D. That is this expression. So that is simplification using our De Morgan's theorem. So the next method here, according to our slides on algebraic simplification, another method is with the use of Karna mapping. So that is pronounced as Karna or Karna mapping or Karna map. So in Karna map, we usually employ a 2 by 3. This is used in a 3 variable K map, and this one is for 3 variable K map, and this one is for 4 variable K map. So this is a K map is a grid of squares, and each square represents the minimum terms, and square on edges are considered adjacent to the square on the opposite edge. So yun here, according to this one, the square on the edges are considered adjacent to the opposite edge. That means the square on this one is adjacent to this one. So yun if you will fold, so if you consider this one as a a sheet of paper, and if you will fold it and form it into a cylinder or a circular cylinder, this edge will join this edge. Therefore, the square here is adjacent to this one, adjacent to the karadarwa. So the same here. If you will fold this one and this one, this red is adjacent to this one. At the same time or at the same manner, this square here are also adjacent to the square here. The uppermost and the lowermost is adjacent. The left and the right is also adjacent. If you will try to fold the map into a cylinder, so the two sides that are adjacent to each other are the edges on or the square on the edges of our K map. So before that, I would like you also to notice how our K map is being uh, written. So take note that in K variable K map, your first variables, so say we have inputs A, B, C. Your A is 0 here and 1, and your BC is on the upper. And take note the representation of our BC. This is 0, 0, 0, 1, 1, 1, and 1, 0. It is not 0, 0, 0, 1, 1, 0, 1, 1. It is not that. It is not arranged in that manner. However, it is arranged at ito, 0, 0, 0, 1, 1, 1, 1, 0. And if you will notice that it is the same while we are in the 4 by 4 K map, your AB is 0, 0, 0, 1, 1, 1, 1, 0. The same here, 0, 0, 0, 1, 1, 1, 1, 0. Because later on, magbaliskad lang dya, your answer in your K map will be already wrong. Sala na dayon kung mabaliskad lang ang assignment ninyo kang inputs nga 0, 0, 0, 1, 1, 1, and 1, 0. So again, that is a reminder to all of us when filling out our K map. So here, filling out a K map. So we are given here an SOP expression for A complement BC plus AB complement plus ABC complement plus ABC. So as we have discussed earlier in SOP, we are employing outputs with 1. So that means this expression, this SOP expression, is already derived from the output, which is 1. These inputs give a value of 1. So here, we are to write 1 in all the squares, which include the term for each product. So again, SOP, this this is 0, this is 0, 1, 1, this is 1, 0, 1, 1, 1, 0, and 1, 1, 1. So how do we write that in our K map? So here, we have here 1, 2, 3, 4. So we have here our, again, this is A, this one is BC. So take note it is not allowed to uh, rearrange our variables. It is always A here and BC here. First input 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. So we have here 0, 1, 1. So A is 0, B and C is 1, 1. So we will write 1 here. Next is A is 1, BC is 0, 1. So A is 1, A is 1, B is 0, BC is 0, 1. So we have 1 here. Next is 1, 1, 0. A is 1, B is BC is 1, 0. So we have here 1. And last is A is 1, BC is 1, 1. So BC is 1, 1. And all the rest of the squares should be equal to 0. So that is how to fill up our K-map. So just do the same if we are in a 4 by 4 K-map. The process is still the same using the K by 3, K, 3 by 3 K-map. So how do we minimize? So minimization technique using the K-map. So ako, I'd rather use K-map than doing the Boolean simplification because you need to memorize the identities or the theorems in Boolean algebra. Where in here, in K-map, you do not have something to memorize. As long as you only know the rules or the techniques used in the minimization using K-map. So we have here the minimization techniques. The minimization is done by spotting patterns of ones and zeros. So depende if you will be using the SOP expression or the POS expression later on in uh, your derived solution or your answer. So if you want your answer to be in SOP, so you use the ones. And if you want your answer later on to be in POS, you use the zeros. So you spot the patterns of ones and zeros, of course, depending on your choice of the simplified equation, whether it is SOP or POS. The second is simple theorems are used to simplify the Boolean description, and of course, pairs of adjacent ones. So here, we are pairing the adjacent ones in K mapping. So in K maps, we have a rule on how to or how many ones should be grouped. So we can group only in a value of groupings can be done in a value of 2 raised to n. That means you could group 2 raised to 0, which is equal to 1. You could group 2 raised to 1 equal to 2, 2 raised to 2 or equal to 4, 2 raised to 3 equal to 8, and so on. So you can group ones uh, as itself, or two ones, or four values of ones, and eight values of ones, which is adjacent to each other. So we will have siguro an example on how to simplify using K-map. So here, uh, in our previous example, we can group this one, two, two here, and two here. Note, do not group terms which are ano nila, already grouped, but you can include those terms which were already part of the group is if one of the terms in the proposed group is not yet uh, part of the group, like this one. So let's go back. Let me just use the K map here below. Our first group could be this group here, 2 raised to n or 2 raised to 1. We could group 2 by 2's. Here, if this is 1, we could group this one as 4. But since this is 0, so we cannot group these 3 because we are allowed only to group 2. We are allowed only to group 4, and we are allowed to group only by 8s, 2, 4, and 8s, and of course 2 raised to 0, one term. We can group this one as solo. However, we have a rule that as much as possible, we will minimize the terms later on in our output. Because say you will group only one here, only one, although we could still use the other one. If you will group only one term, you still cannot eliminate any. So if this, we have three terms here, we have A, B, and C. The power here denotes the term which you can eliminate. So if you will group as say 1, so your remaining term later on will still have three variables. If you will group by 2's, you can eliminate at least one variable. If you will group by 4's, you can eliminate at least two variables in the terms. So why only one? So as I have said earlier, we will try to maximize our groupings in order to eliminate more terms so that our final output will be more simpler. Mas duro ang terms nga gin-group mo, much simpler ang equation nga ma-produce mo. Why? Because later on, these terms can be, or this, your output terms could be translated into a design or into a circuit which can be later on much easier for you to do compared kung duro ang imong variables. So later on, you will appreciate the the value of key mapping or the simplification if you will apply this K map into the actual purpose or into an actual project. So before you group, you try to determine or you try to maximize your grouping. Say we can group this one as itself, but there is an adjacent one here. may adjacent pa ta nga 1 dya, which we could still use as to group. So although this one is already part of this group, but your one here is not part of this group, you could still use that one. So that will be my second grouping. Maximize the grouping here. That one. So we have three terms for this example. So here, cover all the ones with maximum groupings. That is rule number 2. And after the grouping, we have the simplified Boolean expression, AC plus BC plus AB. How did we arrive at this Boolean expression? So that is the question. Sir, paano nag-AC plus BC plus AB ra ang groupings natin nga ra? So we will take a look at those things one at a time. So first, let us consider this group. In simplifying for using the K-map, you look for the variable that is not changing. Ang variable nga wala nag-change. Let us take for example this one, this group. If you will look, what is the value of A of this group? The value of A is 0 here and 1 here. So for this group, our A is 0 and 1. So there is a change in the value of A. If there is a change in the value for the variable, we do not include that in the simplified term. How about the B and the C? What is the B of this group? The B of this group, since they are on the same cell, on the same column, the B and the C is 1, and the C here is also 1. B is 1, C is 1. So therefore, that is BC. So this term here is, the simplified is BC. Let's take another group. Let's take this group. What is the value of A here? The A here is, since these two are on the same line as in the one, so the A is both 1. So we will consider A. What is the B? The B is 0 and 1. Nag-change. Nag-0 kag nag-1. What is the C? Here, the C is 1. The C is also 1. So there is no change. So we have AC. So we have this term AC. AC for this group, BC for this group. And how about for the last group? Let us check. How about for that group? Our A is also 1 because they are on the same plane kang A. So we have A. Next, how about the B? The B is 1 here and the B is also 1 here. So we have B. How about the C? The C is 1 here and 0 radius sa piyak. So we will not consider C because C is changing from 1 to 0. So we have AB. So this one is for AB. That's why we have term AB here. So the simplified Boolean expression for this term is AC plus BC plus AB. So that is how we simplified the term using our Karna map. Okay, let us have more examples of our K-map. So we have here function A, B, C, D equal to 0, 4, 7, 8, 9, and 15. So here we have four inputs, and the outputs of 1 is on 4, 6, 7, 8, 9, and 15. So as a beginner, siguro you need to uh, first translate it into a truth table. So we have four inputs. So we have here A, B, C, D. Sobrang. This one will be our output one. So we have 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 1, 0, and 1, 1, 0, 1, 1, 1, 1, 0, and 1, 1, 1, 1. So here, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. The output is 1 for 0, for 4, for 6, for 7, for 8, for 9, and for 15. And the rest will be 0. Next, since there are four inputs, we will have here also four input K-map, A, B here, and C, D here. So we have, again, don't forget, 0, 0, 0, 1, 1, 1, 1, 0. Hindi magbaliskad, ah. Then, above, we have So 0, 0, 0, 1, 1, 1, 0. So the first term here denotes our A, the second term denotes our B, the first term here denotes our C, and the third term here denotes our D. So CD, CD recommend. So where shall we place our ones? At 0, at 4. So what is 4? 0, 1, 0, 0, 0, 1, 0, 0. So this is 4. 0, 0, 0, 0. 4 is 0, 1, 0, 0, 0, 1, 0, 0. Then we have 6, 0, 1, 1, 1. 6 is 0, 1, 0, 1, 1, 0. 0, 1, 1, 0. So this is 6. Next is 7. That is 0, 1, 1, 1. Next is 8. That is 1, 0, 0, 0. Next is 9. What is 9? 1, 0, 0, 1. 1, 0, 0, 1. And then we have uh, 15. That is 1, 1, 1, 1. Let me check. 0, 0, 0, 0. Okay. 4 is 0, 1, 0, 0. 0, 1, 0, 0. Then we have 6 is 0, 1, 1, 0. 0, 1, 1, 0. And then we have 7 is 0, 1, 1, 1. 0, 1, 1, 1. This is 7. And then 1, 0, 0, 0. 1, 0, 0, 0 is 8. 9 is 0, 1, 0, 0, 1. And 15 is 1, 1, 1, 1. So how do we group this example? So we can group this one, maximize 24, no. So we can group this one, can also group this one, can also group this one, and we can also group that one. So take a look at this one. So considering that this is group 1, so first group we have what is common, what is not changing. A is not changing, but since it is 0, we will be writing it in its complement form because as we have said in the POS, the 0 is written in its complemented form and 1 is written in its true form. How about the B? The B changes from 0 to 1, so we will not consider B. How about the C and the D? So since this is the C and the D, they are on the same square, the C and the D is not changing, so CD. So since again we are grouping only by 2's, that is 2 raised to 1, so if you will notice, we have eliminated only one term out of the 4. So that's why we have still 3 variables here. How about our second group? So plus second group, what is the term? Our A is not changing, our B is not changing. But since A is 0, we are writing it in its complemented form and B in its true form. Because here, you will notice, here this group, this second group is on the same group here. So they have the same A, they have the same B. So A is 0, so complement. B is the same one, so it is written in its true form. And then how about the C? The C for this second grouping is 1 here and also 1 here, so not changing, so we will consider it, and it is since 1 is true form. How about the D? The D is 1 here and 0 here, so we will not consider the D because it is changing from 1 to 0. How about this third grouping? How about the A? Our A changes from 0 to 1, so it will not be included. How about the B? The B here is 1. The B is also 1. So we will consider the B. How about the C and the D? Because they are on the same column here, so we will consider CD. How about here, the fourth grouping? Plus, we have AB is not changing, so A, B complement. So B complement because B here is 0. How about the C? C here is 0. C here is 0. So we will consider C, but in its complemented form. How about the D? The D here is 0. The D here is 1. So we will not consider D. So our simplified equation for this one is A complement plus C complement D plus AB C complement plus BCD plus AB complement C complement. Another one. So we will have next another example. Let me- Now let's have this another example. So we are given the function a, b, c, d is equal to 2, 4, 5, 6, 7, 9, 10, 13, 14, and 15. So Another way to draw a K-map, this is our AB, this is our C. This is 0, 0, 0, 1, 1, 1, and 1, 0. This is 0, 0, 0, 1, 1, 1, and 1, 0. So if you do not wish to draw the uh, logic map or the, what do you call that one? The truth table for the given equation, you can simply have this trick, or you can simply write this one. So directly into the map, this is 0, is equivalent to 1, this is 2, and this is 3. This is 4, 5, 6, 7. This is, take note, this is 8, 9, 10, this is 10, this is 11, and this is 12, this is 13, this is 14, and this is 15. So that is the simplified way to name our map if you do not want to use the truth table. And again, since we are using the SOP expression, so we will be writing 1 on these terms, 2. So the output value here is 1. 4 is also 1. 5 is 1. 6 is 1. 7 is 1. 9 is 1. 10 is 1. 11 is 1. 10 is 1. 11 is 1. 13 is 1. 14 is 1. 15 is 1. The rest is 0. Now, how do we group this one? So as we have said, we have to maximize our groupings. So this can be one group, group of 4. This could be another group, and this one could be another group. So we have 3 groups of 4s. 3 groups of 4s. So we have maximized our grouping into groups of 4s. So let us consider our first grouping, this one. So what is the equation for our output? For first group, what is A? Our A changes from 0 to 1, so we will not consider A. Our B also changes from 0 to 1 because this is 4 squares in a column. We change from 0 to 1, the B also changes from 0 to 1. What does not change is the value of the C and the D. So C and D does not change. So C and D does not change, but the D is 0, so we will write it in its complement form. So take note that since we have grouped it into 4 or 2 raised to 2, we have eliminated two variables or two variable in our input. So what remains is only two variables, the C and the D. Next, plus. How about this group here? The C and the D changes. What doesn't change is the value of our A and B. So A is 0, so it will be written in its complemented form, and B is 1, it's written in its true form. Then consider the last group here. So what terms should remain, or what elements or what variables should remain? Our A do not change from 1 here, 1 here. So A will be considered. The B changes from 1 to 0. How about our C? Our C changes here from 0 to 1, so it will not be considered. How about the D? The D is 1, also here is 1, so the D will be considered. So our simplified equation is CD complement plus A complement B plus AB complement. So that's it for our Karna mapping.